G'day Bifrosters. Welcome to the final video in the scatter series. What are we looking at? Well, this is a flock. Specifically, it's a flock of boids. This is flocking behavior in Bifrost, utilizing the scatter pack. In following with the entire series of this video, I'm not here to show you how to make this. I'm absolutely open for you to dive in and play around with it and see what I've done. And if you find a better way, please let me know. I'm around. You can find me on YouTube. I mean, you're watching this on YouTube, right? So pretty sure there'll be some way to contact me there. This is using the very basic boid system where each one of those boids, which is what I guess they're technically called, are nothing more than a point run through a solver. Some things before we get started, this is not a particle system, this is a point solver. So when we want to make changes, it's always good to snap it back to the beginning, like that. That'll be coming up a lot. Before I go ahead and sort of demonstrate how this works and show you how to use this compound on this node, let's talk a little bit about scattering, and let's talk a little bit about what you would use this for, because at first view this is not a scatter. This is an animated, weirdly fast flock of birds or fish or insects or whatever. The point is that just like scattering, this is manipulating points. This is putting points in positions. It's just that the way this is doing it is it's doing it by giving these points three simple behaviors: a goal and the ability to collide with and avoid obstacles. That's it. So these are not thinking particles. Yeah, I see you over there, Eloy. These are dumb particles, and they're not even particles, they're just points in space. But those points in space each have three behaviors on them. And those behaviors are separation, cohesion, and alignment. You can see them down here, and we'll get into that a bit later. But out of those three behaviors, and the ability to avoid any obstacles in their path, and their burning desire to get to their goal point, which is what they're all orbiting around now, out of those five things emerges all of these patterns in behavior. So there is nothing to stop us going, you know what, I like that frame, or maybe I can scrub forward just a little bit. Don't try scrubbing back, it doesn't work very well. So maybe I quite like that frame. I can grab the points at that frame and I can use them as a scatter. I can raycast them onto a surface. I can use them as a start position or an initial position for a particle setup. I can use them as an initial position for an aero setup and emit fluids from them. I can use them to displace a fluid in organic and interesting ways. I can do an awful lot of things with this, and that's why I wanted to include it in the scatter series, because while it's not a traditional scatter, it can be used very much like a scatter to get good organic feeling movement and good placement organically. And as you'll see when I start to go through the settings, this is so open that you can put an awful lot of different behaviors and looks out of three simple attributes. Let me show you what they're doing before I show you how they work. I'll take you through the settings. So this is the marketing shot. So you're not really seeing what they're doing here. You're just seeing the flocks forming and moving, following each other and playing follow the leader when they don't really have a leader. So if I was to switch that on, things start to make a little bit more sense. So now you can see the obstacles that they're avoiding, and the bright orange dot hidden in here is the point that they're all trying to get to. And I've got them set so that they overshoot the point and just keep the animation going. You can set them to reach that point and die and stop if you like. You can't set it in the settings here, but you can go into here and take a look. And I suppose I better, while that's playing, the reason I'm not going to show you how to make this is that it's quite complicated. It took me a long time to make, and I had a lot of help from the amazing people on the Bifrost team when it was too slow, when I couldn't work out why it wasn't playing nice, and tips and suggestions and all kinds of things. So a big thank you to those guys. That was really good. Learned a lot. But inside here you can see an awful lot of stuff that it's doing. I've left you a lot of notes showing you what each compound, or telling you what each compound does. So if the bounding is empty, generate a bounding cube. averages the positions of the attractor meshes, outputs the point, that kind of thing. And it follows along till you get to the flock solve. And the flock solve is the main solver. It's where everything comes in. So pretty much you can draw a line right up the middle of this compound at this edge, this end here, and everything after that is pretty much just output. Everything before that is input. And that's all I'm going to say about it. Feel free to dive in. Tell me where I've got things wrong. I'm super happy to take feedback. Always. If we can make it better, great. So continuing to play that. That's just they're avoiding their obstacles. And the nice thing about using a solver is that as long as you're playing forward, I can add another 2 attractors. Now the behavior completely changes. I can take the obstacles and I can just move them around a bit. And they respond in real time. I can pull those all the way out so they're not really interacting with them, and push them in, and they start to collide and it changes the shape. All of that kind of thing. You're still getting the nice organic movement that you're using. So the really nice thing about it, I can even just quickly animate those attractors, and they'll follow them around at whatever speed we're doing. I can change the seed of them so they're in different places. They're still trying to follow them around. I can stop the animation, and they're just responding to the center point of those 3 while avoiding those obstacles. Cool. So this is what we're going to be looking at today. And this is the flocking solver. Before we start digging into what this does, let's talk about what it is. So there's a couple of web pages that I want just to really quickly take you through. The first one is the Wikipedia page on boids themselves. The important bit here is that. It's an artificial life program developed by Craig Reynolds in 1986 which simulates the flocking behavior of birds. That is literally what it does. And it does it, as it says here, is the next most important paragraph. Boids is an example of emergent behavior. That is, the complexity of boids arises from the interaction of individual agents, adhering to a set of simple rules. The rules applied in the simplest boids world are as follows. And I based this on the simplest boids world. There are many more complicated things you can do, but this is in the vein of giving you a good starting point. So, the 3 rules, the simplest rules, are separation, alignment, and cohesion. Separation, steer to avoid crowding local flockmates. This picture here. Steer towards the average heading of local flockmates is alignment. This picture here. And steer to move towards the average position of the local flockmates, which is this here. With these 3 rules, I've also added obstacle avoidance and goal seeking. These 3 rules, you can get this kind of behavior, which is similar to what I was just showing you. Excellent. So, I'd recommend going and reading through that to get a handle on it. All of these you can find inside the flocking solver if you want to go look. I believe I've named them well. The other web page I think it's really advantageous to have a look at is this one. In fact, anything that Daniel Schiffman does on the coding train is worth watching. It's done in JavaScript, it's done in code, but the man is an incredible teacher, and I've used several of, my Wally noise, the flocking simulation. I've used several of his videos to help me get through the concept of doing this, and then I'm able to apply it to Bifrost. Really, really good value. I'd recommend this highly. Okay, back to our points, which are just still happily orbiting their goal points. So you can see in the settings, there's an awful lot of settings, and we'll go through them like we have been doing. You can see in the settings that if you come down to the forces here, you've got align force, cohere force, separate force. And again, align weight, cohere weight, separate weight. Those are the 3 behavioral forces: alignment, cohesion, separation, and again here. And the nice thing is that you can get quite a different look with a very small change. So these guys are trying to stick together a lot harder now. So rather than being loose and floppy, they're trying to be a really, really cohesive unit. And you can see that. You can see that. When they're broken apart by an obstacle, they get back together and get as close as they can very, very quickly. And that's just changing the cohesion force. And change that down, and they get really loose and a bit random. They're still following each other, they're still avoiding obstacles, but they're just a little bit more loosey-goosey. Yeah, and it's the same with the other forces. I can double the alignment force, and they're trying a lot harder to all point the same way. Or I can push up the separation force really large, and they're just trying to get out of each other's way really hard. So just as we go forward, just remember that the behavior on these guys is very much controlled by a balance of these three forces. So if I've got, say, a very high separation weight, they're just going to try and get away from each other as hard as they can. You end up with each Boyd here plotting its own path, still trying to reach the goal, but not really trying to do anything with what its flockmates are doing, because they're all separated very, very strongly. If I take that back to point 2, you can see they're all following in line again. And it's the same with the other ones. If I take the alignment weight up, it doesn't really look like it's done much, but they're much more strongly trying to face the same way if I pull the alignment up. And coherence you can think about as stickiness. So you see that they're trying to get as close as possible and stick together. With a coherence weight this high, you're going to eventually end up with a single Boyd, like this is trying to do now. You can see as I reduce that cohesion weight, they spread out to a nice mushroom and then start following each other around again. So you can get a lot of different behaviors just by playing with these three things, but it is a bit of a balance. It's rough. They roughly add up to 1. So if I go through 3, you're getting a little bit of random behavior there, which is, why I had them at the settings I had them. 3, 3, and 2 and 2, 0.2.2. You've also got the max collision turn force. And what that's basically doing is how quickly they turn away from an obstacle when they hit it, or a collision when it happens. You can see they're a little bit jerky, they're bouncing a little bit. If I take this down, they're going to be a little bit smoother, like so. They're quite stupid. They can't actually, they do have a perception range, which is what this is doing up here, which is how far in front of them they can see, or how far around them they can see. But they're still quite stupid. They still tend to run into things, and they avoid obstacles, but not all of them are very good at it. But anyway, I'm getting ahead of myself. What I wanted to illustrate was this is the balance of these three forces: alignment, cohesion, and separation. So you can get a radically different look by changing one thing. You can also make sure it doesn't go quite so fast. At the moment, I'm actually playing this every frame free, so I'm getting 50 frames per second on this. I can speed this up by changing the speed limit. There they go. Much, much faster. Or slow them down. Let's go through the settings for the compound and what effect they have on each thing. So what's it doing and how's it doing it? So here they are, just happily orbiting, doing their thing. Stop that for a minute. Inside the flock compound, you have 3 sets of settings. You have the Boyds themselves, the initial values, and the flock settings. The Boyd settings here control essentially what you're throwing around the solver. So they control things like what are you putting on the point, and quite literally the forward axis, and that's about it. So which way do they point, and what are you instancing on each point? This is using instances. Now all the way through this compound you'll see as we go that for a lot of things I'm giving you the option of plugging your own thing into it. So I can take a mesh cube here, get these playing like so. Because there's nothing plugged into instance mesh right now, what this is doing is it's just using Bifrost internally to generate this. You know what I need to do? I need to fix my alpha channel here. There we go. Internally, it's creating this diamond shape, and I'm using a diamond shape just to show you which way is forward, which way is back. So the noses, the direction of motion is always the white end, and the dark green end is always the bottom, the back. It's always the back end. But that doesn't mean that you have to use what I've provided. These are just a placeholder for you to have a look at, and they're generated inside here. But the reason that these are turning up at all is because I've got nothing plugged into my instance mesh. So if I take this mesh cube that I created earlier and plug it in, everything goes weird and doesn't look right. I'm just going to hide all of the other extraneous things. You see, until I go back to the beginning, reset the solver, and play. So now you've got a cube doing all the Boyd things, including the occasional jittery rotation. But you get the idea. So this is just essentially a dummy Boyd, or a dummy shape just generated to show you what's going on. You can think of it as just like an arrow. And this follows through across this entire compound, is that I'm usually giving you somewhere to plug something in. So this would be a mesh. And then if it's not there, then the generate tab underneath it will just generate something that'll fill the hole for you for now. So the Boyd section is really just describing what you are instancing onto your points, what's flying around in there. And it's quite simple. The forward axis will change which way they're pointing. So see, now that changed the way. They're all trying to point up. And they're all going to travel nice and sideways, which doesn't really quite work for us. So I need to take that back out. Restart the solver and off they go. Being happy little Boyds. So that's about it for the Boyds section. Close that up now. And then we come down to initial values, and this is where things start to get a little more interesting, but also a little bit more the same. So first thing you've got is the point color. So there you go, that point color there corresponds to this point color here. You get the idea. Rid of that now. Back to this. Now here's our first user input that we could use. Points to flock. You don't see it on the settings because it's an input plug. Points to flock is the ability for you to just plug in whatever points you've got. If you've got a particle system that you want to plug into it and then use this to flock the particles, you can do that. If you, like I said before, if you just want to play it forward and then pick a frame you like, use that as the input to a particle system, it works both ways nicely. But this is for if you want to put, this one here is if you want to put in your own point system. So something I could think of for this, if you've got some kind of effect where you want a whole bunch of stuff that starts on the ground to pick up and start moving towards a point, or start flocking towards something, or some effect you're doing, then you can do that by just putting these points in, changing things like the start frame and top speed and all of that kind of stuff, and off you go. So if you've got points going in here, it completely overrides the generate. And it's the same with everything else. If you've got something going into a plug that you need and there's a generate underneath it, the generate gets ignored as soon as you plug something else in there. But in this case, you can see there's an object we're scattering on. There it is. If I change this object size to 2, you can see that the solver changes accordingly. That's the scatter node coming through. So mesh to scatter is, if you want to scatter on a mesh using these settings, plug a mesh in here. It's great. Amount, we all know what amount does. Now I have 250 of them. Now I have 1,000 of them. And now I have 5,000 of them. And off it goes. It's a bit slower, but it's still doing the calculations. Also, I don't have the fastest or newest machine in the universe. All of this is from the scatter pack. So you've got the amount, which we just covered. You've got how that amount is calculated. Is it radius, density, number? Is it random, blue noise, maximal? All standard scattering stuff. You've also got the seed, which is, it's in the initial values. This is the initial position seed. This is the scatter seed, basically, which is great. But you also need an initial velocity, and again, you have an input velocity here if you want. So if you have a bunch of points and they're moving and you want to stop them at a frame, you can take the velocities at that frame, plug them into here, set your start frame accordingly, and it'll start moving as a flock at the point you set it. It's just a good way. You can take the velocities that you already have, plug them into the system, and you've got your animation, your animation, your animation. You hit a start value, and it goes from your animation to a flock, which is great. It's great and very helpful, I think. Again, if there's something plugged into input velocity, the generate ceases to work. So at the moment, I've just given them a random velocity between -1 and 1 on all axes, which is why if we step forward, you can see them start to align. I get the wobbles a little bit because of my settings, but off they go. But initially, they're going in all kinds of random directions. So that's the initial values. And then the main meat of everything, you've got the flock settings. So where this was all about what you're plugging into the system, and this is the initial values of the system, this is now describing how the system behaves. And this is pretty much the meat and potatoes of everything here. Come back here. First thing you've got is a perception radius. And the way that works is you have, say, this void here. Let's pick one that's a little easier to see, shall we? And this will only go here. So this guy, this void here, has 0.5 on its perception radius, which means it's looking in a 0.5 sphere around itself for any other voids that it can base its behavior on. If we play it, you can see it turns towards the other voids because they're inside its perception radius. This perception radius is pretty high at the moment. Do that. And so they're reacting a lot quicker and a lot more decisively when they have a smaller perception radius. Now this of course is dependent on scene scale and all kinds of factors, but essentially this is a sphere of perception around each actor to which it's going to react to things with. The exception is its attraction points. It's going to try to get to its attraction points no matter what, the way this is set up. Cool. Then you have a start frame. I was talking about that before. So if I have some animation until frame 45, and then I want to take that animation and plug it into the voids, these guys will do nothing until frame 45, and there they go. They'll take off and they'll start, and all their perception kicks off and everything like that. So you're able to blend in your own animations, that kind of thing. You've got a speed limit. So I played with this a little bit more before. Let's change that start frame back to 0. 1 rather. Off they go. Cool. Speed limit, it's pretty simple. This limits the maximum speed they can go. There you go. This has some effect on these guys as well, because if they're going too fast, they're not going to register what's in their perception radius quick enough. So again, it's a bit of a balancing act, but you can still get pretty good results out of it. In they go, out they go, round they go. Point of attraction. Now this is if you haven't supplied an attractor and you have 2 inputs here and they're both arrays and they're both set to fan in, basically. So you can plug in several things. Like if I wanted to make the attractors obstacles in their own right, I could plug them in here, they'd turn up. So this is what it's attracted to. It can be several objects. This one at the moment is generating 3. And you can see them as the little flat coloured spheres. There's 1, 2, and there's the third one in there. I think it might be inside a box. No, there it is, just peeking out. So if you put in more than one attractor, it's going to try and get to the center of all of them. So it essentially just gives each one equal weight and heads for the center as hard and as single-mindedly as it can. But if you haven't got any attractors in, you can set what point they're attracted to here. If you've got something plugged into attractors, that's not going to work. And it's the same with obstacles. The difference is if you don't put anything into obstacles, like so, they're not going to collide with anything. They're just going to keep trying as hard as they can to get to the center of those 3 points. You can see how that's working there. So in fact, that's quite a nice little vortex shape going on already. And because I'm a clever person and I've set up a way to change my attractors, you could also do something nice by animating your attraction points. Cool. They're all moving very quickly at the moment. They're very in much of a hurry, these boards. Slow them down just a little bit. It's not going to generate obstacles for you. And that's the only thing, pretty much the only thing it won't generate for you is its obstacles. It's relying on you to put some meshes in there. It's quite happy to take meshes. There it goes. There are the meshes. These are just dummies at the moment, so you can plug your own in quite happily. Everybody's happy, that's how that works. So now we come to forces. We touched on this a little just before. I'm going to speed this up just a little bit. Like this. Sometimes you have to go in and restart the solver. A lot of times you don't. We'll just stick that back to one attractor again. A little bit of simplicity. This is quite frenetic because they're hitting this guy and just breaking apart, but that's okay, we can see what's going on. So, max align force first. If I take that to 0, really does not like that, is not having a good time. If I take it to 1, got almost no alignment at all. So that seems to be reversed. You could possibly think of this as the minimum alignment force. Something to look into. You can basically see that the more you change this, the more they try and line up with themselves. Except they seem to have got this backwards. Which is okay. Then you've got the cohesion force, so how strongly they try to stick together. You can see as I increase that, they're trying to get closer and closer and closer together. Stick into a cohesive unit. And these 3 is where you can change the look of it quite drastically. So if I have that up at about 0.82, they're forming a nice tight, eventually forming a nice tight vertex around the point. They're trying to stick together as hard as they can. The obstacles are getting in their way, as obstacles are wont to do. It's right there in the name. But they're trying to form a cohesive flock as hard as they can. If I lower that number, they get looser and looser and looser. And just losing their cohesion as I get lower and lower with that number. That's pretty much self-explanatory. And separate is almost the opposite of cohesion. Have a look at the separation force. Just this one. Separation force, steer away to avoid crowding local flockmates. So this is trying to get away from the average, well, it's pushing away from the middle point of its flockmates inside of its perception. So the higher the separate force is, the further apart they try to get. And eventually they just become a big singular mess, and you can dial that back. And as you dial it back, you're going to get more and more of a flock. This one you might have to restart for. We're dialing it back, and they're starting to just get a little more. They're not trying to get away from the center of each other's mash as much, and you're just getting. Then you've got max collision turn force again. So if I push that up, you can see that they bounce a lot more. If I pull it down, then they're going to be a little bit more smooth when they hit things. This is all about the collisions, this force. And then each one of these has a weight. So I'm using only half of the align weight right now, just under 0.3 of the cohesion weight and 0.3 of the separate weight. So while you've got the magnitude of the forces, you've also got the weight as applied to the system. And my alignment is definitely backwards, and I'm going to need to go in and fix that. So by using the weights, you can achieve different looks again. So if we have an aligned force but a lot of weight on it, you're getting a nice cohesive flock, but they're moving a lot further out. They're still trying to clump together, they're still trying to get to the goal point, but you're just getting a bit more of a random look. It's quite a good look. Whereas if I pull that down, then they're just going to try and get closer and closer and closer. I need to reverse that. Same with the cohesion weight. As I push the cohesion weight up, it's applying the cohesion force more and more and more. And they're getting tighter and tighter, and as I lower it, they get looser and looser and looser. And the separation weight's the same. So the higher the separation weight is, the more separated they are, the less cohesive, and then the lower the separation weight, they get closer and closer and closer and clump up again. That's how those three work. Like I said, you can achieve a lot of very different and quite good looks with this. And I've just been trying to demonstrate that as we go. But that is a balancing act between all of the forces, includes the collision turn force, how they behave when they hit obstacles, and the weights of each of the three behaviors. Takes a little bit of getting used to. I built the damn thing and it took me a little while to get used to it. But once you do, you can achieve some really nice results with it. Moving on down, we have attraction, and this is how much it's attracted to this guy. So at the moment, it's very sensitive. If I stick that to 0.2 and that to 0.8, you can see what's going on. They are so attracted to that center point that there they go. They don't want to go anywhere. They've all made a nice nest and everybody's good. Let's open that out again. There we go. So that is really quite sensitive. And of course, as you change it, different looks, both subtle and not so subtle. And there we go. Now let's talk about bounds. By default, the flock comes in with no bounds, and if you read the little note down here in the example file, proxy is showing all the obstacles. Turn that off. I'm just going to get the voids. It's also showing the attractors. Let's edit that now. There we go. Diagnostic will show the bounds. At the moment, and by default, there are no bounds. You can plug in a bounds geometry, so a cube or whatever you want. I think it only works with a cube right now. Or you can set up the center of the bounds and the size of the bounds. So just do that, and then we'll enable it. And nothing much changes until one of the voids gets out to the bounds. So let's turn on the bounds and have a look. So I've just changed the way the alpha channel works so that we can see the bounds object, which means our voids are going to look a little bit funny. And so that there is my bounds object. And you can see that these two have popped out of the bounds, probably because I turned them on halfway through the solve, and now they're trying to get back in. And sometimes they'll force their way out, and they're trying to get back in, and they can't. So this probably has a little bit more to do with the way the normals are facing on the bounds, which is easy enough to fix. So yeah, as you can see, it doesn't always work well with bounds, which is why it starts with the bounds off. I would recommend that you don't use them. They're really just there if you really need to do anything. Turn that off. So now you can see they're just behaving themselves a lot more like we set up. And that's pretty much about it. That's Boids. Well, it's flocking. If I was to give a quick example of maybe how I would use this in a scattering scenario. Okay, so let's do something with this. And to do that, the first thing I'm going to do is pull this out. I'm going to just drop the number of Boids that we've got going, just for speed. Just for now. So we'll go to 250. And that's all nice and fast. It's all doing its thing. Very quick. So what I'm going to do is I'm going to put down a plane. And this is just going to be like a ground plane. All good. We'll make it 10 by 10. And let's give it quite a few segments. It's got 200 by 200. So we'll just co-opt this terminal. So we don't need it anywhere else anymore. So there we go. We just got a plane. We might want to make that plane just a little bit bigger. 15 by 15. And what I'm going to do is I'm going to use the flock to essentially draw or change the color of the plane beneath it, well, the plane around it, just to show you how we could use this in a practical setting. So the first thing I'm going to need to do is I'm going to need to get the positions. Oops. Poisons. Get point position. That's the first thing I need. And then I'm going to need to get point count. So this is going to give me the number of points in this plane and their positions. The reason I'm going to do this, I'm going to make a new array by using resize array. This, and I'm going to make that array math float 3. So we've got a nice math float 3 that is black at the moment. And the reason I'm making this is I'm going to turn this into the colors. Now, the reason I'm making a new array is I'm going to use this as my color array. So let's give that a name, so we know what we're doing. And we're going to pop it onto our plane. This is the main thing we're going to do. This sign diagnostic material. Let's give it a color. Let's just say 1, 0.8, 0.6. Some sort of a creamy color. There we go. So yeah, we've just got a nice bit bright, sort of creamy, yellowy color for that. And that's just to get things all set up. We've got an array of colors. So every single one of the points, we're getting the point count, going through a new array, and we're generating an array of these values for every single point. And that translates to this color on every single point of the plane. Which is cool, because what we're going to do is we're going to use the position of the Boids to change the color of the plane. So the next thing we're going to need to do is we're going to need to raycast the position of the Boids onto the plane so that we know whereabouts on the plane the Boids are above. So I can get the point position, I'll get another point position here. Let's get the point position of the Boids like this, which is great. I'm going to do a raycast with my Y, get raycast locations. I'm going to get the locations on this mesh, and we're going to get them at these positions. And now we just need a new array for the directions. Array size. We'll copy and paste the color array, because that is just a resize array. Plug that in, and we'll call this directions. And instead of this, I'm going to go down. So that's just a vector describing down. 0 in the x, minus 1 in the y, and 0 in the z. So let's plug the directions into the raycast. And before we go any further, let's check that this is doing what we want it to do. So I'm going to use a location scope for that. Like that. The location scope wants obviously the locations, and it wants the mesh that you're, the geometry that you're raycasting onto, and the positions that the raycast. As you can see it here, the positions that the raycast from which to draw the arrows, basically. So those are our void positions, which we have. They're here. We'll plug those in as well. And I'm just going to throw that location scope out into the proxy so we can take a look at it. Turn on the proxy, and you can see that we're raycasting straight down onto the plane, but we're doing nothing underneath. We need to change the raycast from semi-line to line, and then I'm going to turn off the cutoff distance. So now, if I play my voids, it's a little slower because it's doing all the raycasting for each frame, but it's tracing out positions on the plane from the positions of the voids, which is what we want. And we're going to use this information to change the color of the plane. So that's cool. Let's turn that off for now so that we don't have to have a look at it. It should speed everything up a bit too. Yep, which is great. Now here's our color array. Let's just pull that down a bit so that we can work with it. So really what I want to do now is, at these locations, it's all very nice to have the scope and watch things happen, but what I want to do is sample a property here. Like this. Sample property, yeah, it's not happy because it doesn't know what it's doing right now, and it's also got locations plugged into geometry. So if we check this, geometry, the geometry on which to sample, now that's our friendly plane. Drag out another one of those there, and we want to sample the position. There it is. I'm going to go and make that a float 3 because the position is a float 3. So this is now sampling the positions of each of these location hits, and if you remember that this, what it's basically doing is sampling a position on the plane for each of these circles here. So everywhere the ray hits and underneath as well. And that's the positions we want to do things to. What I want to do is I want to get closest point. And it's pretty much doing the same thing. We're just going to use this here. Oh, my bad. I did want to sample those positions because then I want to put them into. So once we've sampled the positions, we can put that straight into get closest point. And this is doing very much what the raycast is doing, but without the rays. We need to get another version of this. I'm just going to put a pass note down here because it's starting to get a bit octopusy out there. There we go. Put that in there. And we can check this out with our location scope too if we want to. So I'm going to plug these locations into the scope. And I think I'm going to need to plug in those positions. There you go. So you can see that it's sampling the closest point to those hit positions. Yeah, and what we want to do is we want to change the color on that point with a solver. Now, I have a solver here, a color solver, that I've already built. I'm not going to build it again. But to give you an idea of what it does, it's really, really simple. It's making itself a start frame, so it's saying if I am less or equal than whatever this number is, then we're going to pipe into point colors. So whatever comes into here. So if that is if I'm less or equal, if I'm not less or equal, so if I'm greater than 0, I'm going to plug in this input, which is the port state from here. And all this is doing is setting this index in this array, or these indices in this array, to this color. That's all it's doing. And then putting that back out, which then gets fed back in here through the port feedback. And away we go, and around we go. So basically this is just changing the color to this. And all I need is the point color array, which I have here. So there's the color array that comes in here. And the indices that it says inside footstep because it's from another file, but basically the indices that I want to change on this array, on this color array. So we put the point indices in there, and we'll move these along a bit, and I'm going to turn off the scope again for a bit of speed because this is not the fastest thing in the world. Turned off the wrong thing, didn't I? So what comes out of here is a math float 4. I need that to be a math float 3. So I'll put down a vector 4 to vector 3, which is just going to throw away the W value for me, so W value being the alpha channel. And then I'm left with something that this diagnostic material compound can read quite happily. We pop that in there, and it immediately goes black. And that's because we are working with two solvers now. The big solver in here that's doing the flock information, and the little color solver here too. So we need to reset those solvers. And you can immediately see that I've got this blue color all the way around here on the first frame. And if I play this, there you go. So that's just one example of a practical use for this in terms of scattering. What I'm doing here essentially is scattering those colors on that surface from those voids. And in this case, it's possibly not the best lookable, but it's kind of like a nice big splotch. But you don't have to scatter color. You can deform the surface. You can, like I said before, you could add the velocity of these to an arrow setup and get some organically moving motion in fluid. But there you go. There's a practical use for it. It's quite abstract, and it does all of these ray casts and samples, and closest point is slowing everything down a lot. To speed that up, you might want to move your voids off into a different file, or calculate the accelerators differently. I'm just doing it this way to show you guys sort of on the fly how that would work. Alright, so there you go, that's flocking. Feel free to go nuts with it, pull it apart, have a good time. Love to get any feedback that you might have. Please reach out and let me know if you found something, or if you found a better way to do things, or anything like that. Obviously these would look a lot better if this plane was a much higher resolution, but it's, it's gone from over 100 frames per second to 12 already. I don't really want to just sit here and slow this down anymore. So yeah, I'll leave you with that. Hope you've enjoyed all the scattering stuff we've been doing. Hope it's helped, and yeah, have a good one. Thank you very much.